ናችሁ? ዛሬ ኢንተርናሽናል ዴይ ኦፍ ውመን ኤንድ ገርልስ ኢን ሳይንስ በሚል መሪ ቃል ኢንተርናሽናል የሚከበር መርሃ ግብር አለ። ይሄ መርሃ ግብር የሚከበረው በጀንደር ስቴም ፊልዶች ላይ በተለይም ያለውን የጀንደር ኢኒኳሊቲ ጋፕ ለማጥበብ ኢንተርናሽናል ይከበራል። ኢንተርናሽናል አስትሮኖሚካል ዩኒየን ኦፊስ ኦፍ አስትሮኖሚ ፎር አውትሪች ይህን ፕሮግራም ኢንተርናሽናል ዴይ ኦፍ ውመን ኤንድ ገርልስ ኢን አስትሮኖሚ ብሎ ያከብራል። ኢትዮጵያ ስፔስ ሳይንስ ሶሳይቲም ይህንን ፕሮግራም ነው ወደ እናንተ ይዞ የቀረበው ዛሬ። ስለዚህ ዛሬ እንግዳ አለን። ወይዘሮ ፌቨን ማርቆስ ትባላለች። ራሷን በኋላ ኢንትሮዲውስ አድርጋ የምትጀምር ይሆናል። ዛሬ የሚኖረን ሴሽን መጀመሪያ ጀነራሊ የእሷ ኤሪያ ኮዝሞሎጂ እና ጋላክሲ ኢቮሉሽን ላይ ስለሆነ እና ኦዲየንሳችንም ዳይቨርስ ስለሆነ ሁሉም ሰው የሪሰርች ኤሪያውን በደንብ እንዲረዳ እና ሴቶች ሞር ሞቲቬት ለማድረግ ወደ እነዚህ ፊልዶች መጀመሪያ ፕሬዘንቴሽን ይኖረናል። ከዛ በኋላ ኢንተርቪው እና ስለ ፌቨን ማርቆስ የሪሰርች ኤሪያ የምንጠይቅበት ኢንተርቪው፣ እንደገና ኤክስፒሪየንሷን ሼር የምታደርግበት ፕሮግራም ነው የሚሆነው። ቀጥታ ወደ ፌቨን አልፋለሁ። ራስሽን በሰፊው በኋላ ስለ ራስሽ ሞር ትነግሪናለሽ። አሁን አስተዋውቀሽ ወደ ፕሬዘንቴሽኑ ማለፍ ትችያለሽ።
እሺ፣ ስላይድን ሼር ላድርግና አይ ቲንክ አና አንኤብል ቱ ሼር ስክሪን ይላልና ስለዚህ ሆስት ኦኬ ቴንክ ዩ I think for international audience, it's not easy to use Amharic for like scientific terms, but to introduce myself, my name is Feven Markos Hunde, so I am a final year candidate of PhD in astronomy, specifically in cosmology. So at Center for Theoretical Physics in Poland, in Warsaw. So thank you guys for inviting me and to give me this opportunity to share my experience and like my experts' view. So to start with, I think you can see my slides, right?
Yeah.
So, okay, to start with, and to give just a brief like overview of cosmology, it's one branch of astronomy. So, and it studies about the origin or formation of the universe and how structures form and evolve inside the universe and also the universe itself, and the final like fate or future of the universe. So we have different hypotheses like how the universe will end, but the whole study of this is like cosmology. So it's a big and wide field. So it starts from the beginning up to like the future in the current also. So inside this, we will study different structures. So it will explore like larger structures like galaxies, dark matter, the cosmos, cosmic wave, and also like small, like in case of cosmology, small structures will not go like up to stars, but up to like satellite galaxies inside the bigger galaxies. So we studied these structures using cosmology. So this is a field of the study. So when we come to the universe, like commonly we will assume like to explain like the universe for public audience. For example, we will assume like a cake. So when we test the cake, we know that like sugar is there, like different ingredients and recipes are there, but we don't know like in detail, or we can see them, but we can like test right the existence of those ingredients in the cake. So the same like for the universe, we can't explain or see like especially most of the components of the universe, but we know that they exist there because they have interaction with the normal matter, or we can see using different evidences. So like in broad way, we will assume that the universe consists of normal matter. So everything what we see, like stars, gases, planets, people, everything. So that consists only 5% of the universe. Then the other like 95% is unknown. So the other component is dark matter, which is like as a glue. and it consists like the largest matter distribution, around like 85% of the matter distribution, also 25% of the universe. So we know that it exists because of different evidences like gravitational lensing. Gravitational lensing means, like, for example, when we see by telescope, we will see those regions are empty, but there is a bending of light or the change of direction of light in those places because there is a gravitational interaction. So we know that because of this and other reasons like cosmocluster and other evidences like CMB, we know that dark matter exists, but we can't see it by telescopes because it doesn't have any interaction with electromagnetic light. It interacts, currently we assume it interacts only using gravity. So that's dark matter. The another component is dark energy, which consists of like 70%. So it's the biggest one, but we don't know. We assume that it is the reason of the expansion of the universe, but we don't know in detail. So people work on this in other like things also. So we assume these are like the main components of the universe. So when we come to like cosmology, I try to generalize like the big questions of cosmology, but we have like in detail more. So the first thing is how the universe begins. So we will assume that the universe began by Big Bang. This is like our current knowledge. We don't know in the future if it will change or not, but we will assume the universe began with Big Bang. Then it evolves. We will try to study this. So the cosmology tries to answer these questions: how the universe began and what does it look like at the beginning. And the other is what is the nature of dark matter and dark energy. As I told you, like we don't know like 95% of the components of the universe. So we try to understand how these like components behave, what is their nature, their properties, and things like that. The other thing is how the universe evolves to the future. As I told you, like we will assume different like fates of the universe, like big freeze, big rip, or big crunch. It may like expand. It will continue expanding for like until it will become like cold, empty, but it will continue expanding, or it may also like condense it back. If the gravity is bigger than the expansion rate, it will condense it back and it will be like a ball, like a hot dense ball again. And the other one is maybe the structures like the galaxy stars will fly away because of the expansion rate if it's higher than the gravity. So that may be another fate. So we estimate different like fates of the universe in the future. So cosmology tries to answer that also. And the other one is, are we alone in the universe? We don't know that. And there are like big missions like in different organizations like worldwide to study this. So are we alone in the universe, or are there other living organisms or living creatures in the universe? So cosmology tries to answer like this and other like big questions. So how cosmologists study the universe? The first one is they use telescopes or space missions. Like these telescopes can be ground-based or like space-based, as you know, like the famous Hubble, James Webb, or Euclid will be coming. So there will be also like ground-based telescopes. So they will use this to study the universe. The other one is large scale surveys. It's a survey, but mostly these are like ground based surveys. So these are the famous ones. In LSST is coming, I think it will be coming this year. So this and other like large sky surveys, which will cover like some part of the sky, like maybe the northern part or the southern part, or half of the northern or half of the southern part. So we will use these large sky surveys to study the universe. And the other one is using simulations. So as I mentioned earlier, we don't know like how to see like dark matter because it doesn't have interaction with electromagnetic light. So we assume that it exists there. So we build simulations based on like different theoretical modeling. So we will try to understand also dark matter in galaxies using simulations. So using supercomputers, we will do that. So there are famous like simulations like Illustris, Millennium, Coco, Phoenix, Aquarius, and a lot. So for example, you can see here Cosma. Cosma is like a big supercomputers in Durham, UK. So they have like different versions, Cosma 5, 6, 7, and everything. So using these supercomputers, they try to study the universe by building like the universe as like by using these supercomputers, they will build like universe in as a simulations, and they will try to study different structures like galaxies, dark matter, halos, subhalos, and cosmic wave, and other structures also. So when we come to like to see different institutions and collaboration, it's difficult to list. But for example, we can start from SSGI, like Space Science Geospatial Institute, the current Space Science and Geospatial Institute in Ethiopia. I know they have astronomy department, so they may not have a specific cosmology research group, but like including Shambal, many people have studied their cosmology. So they have, I know that. And the University of Cape Town, also Northwest University, Champel is doing his postdoc, I think, there. And also Professor Amara, you know, him also famous theoretical cosmologist. He also works in Northwest universities. In Poland also we have not that much, but like few institutes like CFT, Center for Theoretical Physics, which I am studying there. Then the Nuclear Research Center also, they have cosmology groups and others also. And in UK also, like the famous Durham is because they are so famous because we had a lot of like simulation from there, like as I mentioned, the Millennium, like Flamingo, Coco, and others. Also UCL and others, and many like worldwide also. So if like institutes have like astronomy and astrophysics research group, we will assume they will have like cosmology research group, even if they have like one or two researchers there. So also when we come to collaborations and associations, there are a lot, like there's kilo degree surveys for most will go. Some are like currently working and some are like planning for future surveys. Some of these may work only on observational data, some of them may work only on simulations like CLUES. But there are a lot of like big and small collaborations, and also scientific like networks like Cosmoverse. It's like it's not specific for collaboration of some studies, but it's like a scientific network. So it's under Costa in Europe, but there are a lot of collaborations and associations which work in cosmology all over the world. So it's easy to access. So why cosmology matters? As I mentioned, like cosmology tries to answer like big questions. So expanding our knowledge of the universe. So trying to understand the origin, like how galaxies form, evolve in other like structures also like satellite galaxies, dark matter, dark energy, trying to understand the cosmic wave, the large scale environment. To understand this, cosmology really matters. The other thing is to understand also like the evolution in the change of these properties in a long term and also in the future. So cosmology really matters because of these reasons. Also, it will help us to drive innovation in technologies in the future. As you seen like in the past few years, we had like discovered or we found a lot of like things as including the gravitational waves, right? So these were like predicted long time ago, but when the technology really develops, these things will be easier to be found or to be discovered. So it really like drives the innovation in technology. Also the simulations, as you can see, like in the past, maybe we are using to build like small simulations using like 10 mega per sec or 50 mega per sec box sizes. Now we can, I think currently we have like the biggest ones like in 100 like gigabytes or gigaparsecs or like 500 megaparsec size like simulations we have like Millennium. So this really improves based on because of the innovations in technologies. Like it's two-sided like development. If the innovation in technology develops, it will help to like to work in cosmology more. And also if cosmology develops, it will also will be helpful to like drive the innovations. So this will be like a two-sided like advantage. So because of this and other reasons why cosmology really matters. So thank you.
Thank you, Feven, for the presentation. So let's see if there are questions from the audience before proceeding. So any questions?
Yes, I have one question. Yes.
Okay, yeah.
Yes.
Okay, we say that uh, uh, dark energy is more than the others. That means dark matter and ordinary matter. So if so, why nearby galaxy are merged if dark matter is high?
Can you repeat your question, please? I didn't understand. Sorry.
You said that dark energy is high. That means more than 70, around 70%. So if so, why nearby galaxies, for example, the galaxies are merged together?
Okay.
So
So
why they merge? Or you if they you mean or if they are nearby the gravitational energy is greater than dark energy or what?
okay. So
Yeah.
you are asking me if like the inverse component, when we see like the inverse component, dark energy consists like 70% of like the inverse. Currently, we assume
Yeah.
because of lambda CDM model. So if we assume that when we come to like small scales and big scale, there is a difference. So when you are talking about nearby galaxies, we are talking about small scales, right? So even like for smaller scales, the gravitational force is not smaller. When we are talking about in larger scale, we are talking about these things, right? Even in large scale and in small scale, the homogeneity in the isotropy is different, right? In large scale, we assume the universe looks like homogeneous and isotropic. So if from every direction and every place, it looks like the same. But when we come to small scales, it's not true. So we can see like galaxies. Even for example, if we see like the structures inside Milky Way or Andromeda, they don't look homogeneously distributed or like isotropic. So the same thing, like so when we are talking about dark energy, we are assuming like in the bigger scale, like in the total the universe, we will assume dark energy is higher component. But when we come to nearby galaxies, the gravitational interaction between like satellite galaxies inside that galaxy or galaxy to other galaxies bigger. So I think that's mainly like the study of this peculiar velocity and other things. So that's why like we can see in the nearby like galaxies, we will see the gravitational interaction looks greater. Also dark matter contributes for this gravitational interaction.
Thank you. Maybe another
Okay.
on the slide how to state how the cosmology stated the universe. You mentioned three things. I don't want to understand the difference between the first and the second.
This one's.
No, how cosmology stated the universe.
Are you asking me about this slide? You
No,
mean?
no, no.
Okay. This one? Which one?
I guess.
This one?
This one, the second and the third, what the second, the first and the second.
Oh, the first and the second more, I mean, as I mentioned earlier, they look similar, right? Because when I mentioned about telescopes and space missions, it's like it can be ground based or space based telescopes, but when we talk about large sky surveys, commonly these are ground based telescopes, and these are I try to differentiate this because when we talk about telescopes, commonly they are like based on the spectra of the light. For example, they can be X-ray telescopes only or like optical or others. When we talk about large sky surveys, commonly this is based on like the part of the sky, right? For example, some will study like the southern part, some will study only the northern part, or even in half part of the south or things. But large sky surveys commonly they are ground-based, not space-based telescopes. That's why I try to differentiate this. But commonly, but you can say like this, the second one can be a subset of the first one.
Okay, okay, thank you.
And we have one more question in the chat. I think it's from Dr. Shambal. Yeah.
Can I speak? Yes.
Yeah.
Thank you, Heaven, for your nice talk. Very short and very precise. I was salivating to, I was expecting to talk about like more about your research and dark matter, how the research is going on there. I really appreciate your talk. So my question is just to for you is, can you say a little more about what is the dark matter and its contribution for the governing universe structure formation and related to this sigma 18, currently, which is a hot issue in cosmology. I mean, if which kind of model you are using basically for simulation, because this lambda CDM is a wonderful model, which is very successful model in cosmology, in modern cosmology history actually. It is all limitation. It has a huge limitation indeed. So do you looking for another model which is uh, has less problem in cosmology than lambda CDM. Lambda CDM in physics has not a problem, but when we come to the behavior of the universe, it is very dynamic, and this lambda CDM has some limitations. So can you a little bit more talk about this? Thank you so much. I am happy by your talk.
Thank you, Shamba, for your questions. Okay, to start with your first question, I'm sorry because I shortened my talks because we mentioned it will be like only flash talks. That's why. So to start with, like dark matter, as I mentioned, it consists like 25% of the universe component, but it consists like more than 85% of the matter component of the universe. So it's literally the biggest matter component in the universe. So it serves as a glue. As I mentioned earlier, maybe I will have like some additional slides to show here.
All right. Yeah.
So lambda CDM predicts that like the total component of the universe is lambda predicts for dark energy, and we assumed cold dark matter, right? So cold dark matter means the particles are collisionless and they have negligible thermal velocity. But so when we talk about matter, we know that dark matter existed there because when we see, for example, from CMB is like a picture of from the universe when it was so earlier, like in early age. So as we assume, it's not totally homogeneous. So there are like small fluctuations. That's why you can see like this bluish and reddish like colors. So this dark matter, that means at the beginning we assume that dark matter is there, and because of these small like perturbations derived because of gravity and helps to form structures in the universe. So dark matter really contributes for the structure formation in the universe from the beginning to like the current state. Also, we assume that lambda CDM predicts that galaxies are hosted or formed inside dark matter halos. These are clumps of or self-gravitated dark matter halos. So the galaxies form and evolve inside these dark matter halos. So they really contribute for the properties of galaxies, also their evolution. So there are also like different evidences, like for example, when you see like the coma cluster, we will assume like when two galaxies merge or like collapse, we can see the gravity, like the brighter region or the electromagnetic lights look like they are like less massive, but we can see there is a gravitational interaction which we can see using telescopes or like electromagnetic light. So we know that dark matter exists there. Also another from like velocity radius relations, when we see like we can measure the mass of the galaxies from mass light like abundance, right? So from when we measure that, we expect the galaxies to be lighter. But when we measure from their like electromagnetic light, but they are not lighter as we assume them. So they are massive. So their velocity looks like constant. So this is because of the contribution of dark matter inside the galaxy. So because of this and other reasons, we will assume that dark matter exists and it's a big glue like for structure formation also in the universe. So for my case, in my simulation, we are using both cold dark matter and warm dark matter because we have also different options of for other audience. We have different options of dark matter models, not called dark matter and warm dark matter only. We have like self-interacting fuzzy dark matter models and others. So I think you can find them online, some reading materials. But for our case, we are trying to study in cold dark matter and warm dark matter model. As Shambel mentioned, like this lambda CDM model is the most successful like model currently, but it has like some backlash. So maybe for example, the too big to fail problem, some like dark matter halos are like so big, but they don't like host galaxies as we expect them. So there should be some problem. So we will try to see other options of dark matter models. So we try to see like in warm dark matter model. So especially for small scale structures, like looking other models of dark matter is important. But for our simulation, we see both cold dark matter model and warm dark matter model.
Thank you so much.
You're welcome.
Yeah, thank you, Feven. And Jafar is also asking a question in the chat.
Okay.
Yeah. And you can also unmute and ask if you want.
Okay, I will try to give some comment, but I'm not working in gravitational lensing, but I will try to comment a bit. So I think Jafar's question is to say something about dark energy, lambda. So that represents dark energy in the study of the universe, especially in strong gravitational lensing. So I don't work a lot in like dark energy, but from general cosmology knowledge, that is the main reason for expansion rate of for the current expansion of the universe, because we assumed that the universe was like at some state it was literally dominated by matter only, and at some state it's dominated by radiation. Then at some state there will be equality of dark matter and radiation, but currently we assume like the dark energy is the dominant component. So I think I have it like here. I don't know if we can see. So as you can see, like this is the evolution of the universe, right? Starting from the Big Bang to today's time. So at some point, the radiation was the main driving like force of the evolution of the universe. Then at some point there was like matter radiation equality. Then after that, matter is the one which was driving the evolution of the universe. But after some point, including the current time, we will assume that dark energy is like because the driving like component of the universe, because we assume from Hubble law and others, and we have different evidences that the universe is expanding like exponentially. So this is driven because of lambda. So lambda is representing dark energy, but we have different options. I think Shambel works on that also, Amara also works on that. So there are different options of like dark energy like model, but currently the standard model assumes dark energy is represented by lambda, and that's the strong like driving component of the universe currently, or I mean the today's universe. So when we come to gravitational lensing, commonly I know that gravitational lensing is also more related with dark matter, because as I mentioned earlier, gravitational lensing is like it's changing of the direction of light because of gravitational interaction. So it's not because of the gravitational interaction of only the galaxy which we can see. It can be like other matter components. So we assume because of gravitational lensing there is another matter component, and we assume that there is dark matter, and dark matter is the gravitationally contributing. But I don't think dark energy has that much contribution for gravitational lensing, in my current knowledge.
In my opinion, the cosmological constant has a minimal effect on the gravitational lensing. Dark matter has more influence on the gravitational lensing, especially this strong gravitational lensing, because the behavior of dark energy is driving the universe to be accelerating and expansion, not bending. This bending of light is coming from the geometry of space-time, which is has the object has more warped the space-time due to high gravitational effect due to their mass. So my little comment is cosmological constant has a minimal effect. I can say like that.
Thank you, Sean.
Yeah, thank you, Feven. And if we don't have further questions, we can proceed to the interview. Yeah, so we have a lot of questions for you. So we want you to talk more about yourself, your institute, your research areas, and so on. So yeah, you can see the slide here, and this is a theme for this year's event. So the first question for you is about you. So tell us more about you and your institute, and later we will talk about your research area. So first, tell us about all your academic journey and the institute you currently work in, and we will proceed to the next questions.
Oh, okay. So I started my academic journey by studying engineering, not astronomy. So I started by studying electrical and computer engineering in Addis Ababa University. So then since like my middle school, I am interested in astronomy, but as you know that we don't have undergrad like fields in Ethiopia in astronomy. So I joined electrical and computer engineering. Then after that, I got scholarship in SSGI, like the current SSGI, but the former Ethiopian Space Science Technology Institute. So I studied my master's in astrophysics and astronomy. After that, I got PhD program here in Poland, Warsaw, so at Center for Theoretical Physics. So I joined the Computational Cosmology Group. So I am like currently I am finalizing my PhD. So I'm working in computational cosmology, majorly using simulation to study different structures. So our institute is like it's a research institute. It's not like a university. We have only PhD programming above that. So we do like research in different physics like fields, not in cosmology. We have like relativistic astrophysics, astronomy, quantum computing, and light matter interaction, and other like research groups also. So our cosmology group is one of that. And in our group, we have both observational and theoretical people. So that's the general background.
Yeah, so let's proceed to your research areas. So you have given us a broad overview of cosmology. So tell us a bit about your research topics and the projects you're currently working on, and why this research area, and what are you expecting to answer with this research? And you can also share your screen and show us some results of your work.
Okay, I will. Okay, so when I want to study cosmology, but after like finishing my master's, I was so interested like in studying like the large scale structure of the universe. As you know, it looks so interesting. Also, we have a lot of questions to answer. So I was so interested in cosmology, but I was not like interested specifically on this research topic. But when I found this like research grant, this research position, it's like already decided by my PI, by current PI. So my supervisor, he found the grant for that study. So I started studying this area of study because of that. So mainly my current area of study is trying to understand the effect of the large scale environment. As you can see, the large scale environment, it's not totally homogeneous. So you can see there are some brighter regions. There are also some emptier, which look emptier regions. So this, we call them like cosmic wave. So I try to understand how this large scale structure environment affects the properties of galaxies or halos inside them. So how does the halos or the galaxies behave under dense regions like in these darker ones, or in the brighter regions like in North or filaments? So the main question is I am trying to understand that based on this environmental location, how their properties, their abundance, or their internal structure behaves. So I am trying to answer that, like in general. Also, I am trying to understand how these small scale structures, especially subhalos, will contribute for dark matter search, because currently we don't know like the specific nature of dark matter. It's like candidate components in things like that. So we have like different option of studying this dark matter and trying to detect. So one is using indirect detection. So I am trying to understand how these substructures or subhalos will contribute for this dark matter study, especially for indirect dark matter detection. So to show you some results, I think there are some like published results, as Lydia, I think, show one. So one thing is like, as I mentioned earlier, dark matter structures found like a self-gravitating or a clump of structures, right? So lambda CDM predicts that small structures first form and they will merge or accrete together and form the bigger ones. So inside the bigger ones, we expect to have like small substructures or we call them subhalos to exist at the end or at the present time. So I am trying to understand how their number or abundance will behave in like different environments. So for example, sorry, to show you the environments here, you can see like this is the large scale environment. So you can see there are elongated structures here, longer structures, we call them filaments, or there are like brightest or denser regions like cluster or north, or some are like flat structures like walls, or some look like literally empty, but they are not empty, they are under dense regions, voids. So I am trying to understand how subhalos behave here or here or like here or here, but this is using simulation and this is from observation. So in both cases, you can see this large scale structure. So I'm trying to understand subhalos, how behaves like in these environments. So one of our results is like their abundance really their abundance is really different in different environments. As you can see, like the orange one shows the subhalos which exist in like filaments, in this one exist in walls, or in the red one you can see in dark red they exist in voids. So their abundance is different. This is in comparison to the whole volume of the simulation. So you can see like there is a difference in each line, right? So their abundance is different. Also, we found out their concentration or how they are compact is also different in the location of their environment. And my current also work is how they contribute for dark matter search. For example, we expect there will be decay or annihilation of dark matter. So from that, we expect signals like gamma rays. So when we see these gamma rays, the subhalos or these substructures which exist in filaments will contribute. See, as you can see, they contribute more than the ones in voids or in walls or the ones which exist in under dense regions. So they have also a contribution for dark matter search also. So our current result shows that. So this is my general like area of study. I don't know if it's like specific.
Yeah, it's I think Tahir is also asking a question whether if the previous simulation was your result. Yeah.
Yes, it's my result.
So we can say that you're specifically working on the subhalos rather than the other structure of the filament.
No, I am studying currently on subhalos, halos. So in filaments, in walls, in these are also like the contributions in the environment. So I'm studying specifically on these ones,
Okay.
not in galaxies, like observational galaxies, but a simulation of these halos, say subhalos in this large scale environment.
Yeah. Okay, so let us proceed to the second question and let's talk a bit about your methods and the tools you're using for this research.
Oh, okay.
Yeah.
I think I should go.
Do you like to share your screen or?
Yes, I want to show you some
Yeah,
of like the rays. Sorry.
it's fine.
Okay, so when we talk about methods, we should differentiate two things. The first one is like our simulations. For this one, we have like simulation, right? So for our case, it's specifically dark matter only simulation. We are using COCO. This was run by my supervisor when he was a postdoc in Durham. So I am using this simulation. So we have, as I mentioned, we have both cold dark matter and warm dark matter like flavors, but I am using the cold dark matter one in this specific work. This is one of like the methods which I am using or the contribution, the methodology. So the other one is we use algorithm to classify the environments of large scale. So to say that these areas are filaments, these areas are voids or walls or nodes, we use like a specific algorithm to classify this one. So there is a famous nexus-based nexus plus algorithm. I think you can find the method. It uses different components or like density or velocity as input, and it will classify the environments and will give you like these specific environments. But we updated this one and we built the cactus. This was built by one of our like former postdocs. Now he is in Portsmouth. So it's built by him. So we use this cactus algorithm to classify these environments to different like this cosmic wave to different environments, to walls, filaments, and things. So mainly I use COCO simulation suite and I use Cactus cosmic wave identifying algorithm.
Okay, I think we have a question from Trumpet in the chat. Yeah, any promising? Yeah.
Um, yeah, can I speak, please?
Yes.
Oh, I wanna say, dark matter and dark energy is the most exotic component in the field, in the universe, which is very strange, actually. So, is there any promising finding for the future in dark matter physics? Like, um, it's a big fan, so just.
Yeah, one thing I learned from like science is it will take time. We will discover things, but it will take time. As you know, that gravitational waves were like predicted by Einstein like 50 years, 60 years ago, right? But it is discovered in 2018. So maybe when the technology develops and like when the space missions in the surface develop, I think we will. Also, like in our first paper, we tried to answer one of like the problems. I don't know if you are familiar with one of these small scale problems, like too big
Yeah.
to fail. So we like our results showed that if we consider environments in like subhalos in different environments, they will answer this too big to fail problem. For example, we will assume Milky Way exists in walls or filaments from
Mm.
our result. So if the like the subhalo is existing in walls, it may have like less number of like satellites than the ones in filaments. So I think it will contribute something for dark matter study, but we can't directly predict if it solves the future or not.
Maybe the current law of physics has a problem.
Yeah, that's why I think we don't know. We can't say specifically, but that's why we are trying to see like different options of dark matter models, right? Currently, people are working on different dark matter models. Like I think I know from University of California, people working like fuzzy dark matter models a lot, in self-interacting dark matter models a lot, because they are trying to assume that maybe cold dark matter model has its problems, so maybe considering other dark matter models will solve this problem. Or the same for like dark energy, right? We are using different
Yeah.
W in calculating that also.
Yeah.
Maybe.
Thank you so much.
You're welcome.
Just not for you to explain for the audience what is the depth of the dark matter is look like.
Exactly.
Uh,
Yeah, thank you. So let's talk about your research routine. For example, for some researchers, it's more of work in the computational work, and for some, they have to travel and go to observatories and take part in some observation. And what is your research routine like?
Okay. I think one thing common for every researcher will be starting from literature. So like taking time to read literatures, especially making you familiar with like the current updates and the current results will be help you to understand what is the research gap. So when we find the research gap, it will be easier to understand. So I start from literature review commonly. Then after that, I will try to find out the gaps which I am trying to answer. After that, I will try to formulate a hypothesis based on that. Like for example, I want to answer this questions, and I will have like the hypothesis of maybe this will be this and this will not be this, or things like that. After that, I will go to simulation and analyze a big data set. So like they will be in like terabytes and gigabytes, so I will try to analyze those data sets using like programming language. Commonly I use Python and sometimes Fortran. So I will try to analyze data based on that. After that, if we find like results, especially reproducible results, we publish on papers or we present on conferences. So that's the common thing I usually do.
Yeah. Okay, thank you. So I think we have a question in the chat, but since I have a similar question, I can ask you all together at the end.
Okay.
Yeah, I think we've talked about your research experience. So let's talk about the challenges you faced. For you can speak that in general. What is the challenge when you study cosmology? Yeah.
I think the one thing is the general like challenge for everyone, not specific for me or someone who is working in my research group. The general one is like the problem of like the data analysis is not easy, and the other thing is access of data also. I mentioned, we have like different collaborations, right, all over the world in different surveys, but it's difficult to be member or to access their data. It's not easy. And as a woman of color, it's not easy at all. Like, for example, sometimes people will not open their ears to listen our like research, our results, or our ideas. So we should convince them like it's not easy. So these are the common challenges, not specific for me, but it's a common thing which I usually see them like daily.
Yeah, I think I have also some numbers. If I can share my screen, it will
Okay,
also,
sure.
yeah. Yeah, there are a lot of researches on this gender gap between male and female when it comes to research. And yeah, next slide. I think it's the slide at the, yes, this one. This is just one of the researches out there. So there is a huge gender gap. For example, when we talk about STEM fields, here you can see the graph. this one. This graph shows the number of, it's a comparison between the number of women and men studying or graduating on STEM subjects. So we can clearly see the difference. And when we go from year to year, this is from 2050 to 2022. So there is a very slight change. Even if we can say that there are improvements in some aspects, we can still see a huge gap when we talk about STEM fields. And here, the second graph, we have like 26% of the STEM workforce, women only occupied this 26%. So there is a great gap here. So what are your comments on this? You've also stated some challenges before. And what do you think about this? And how can we address this gap, or can we work on the equity when it comes to STEM fields?
Yes, I think the problem is different for us, like as a developing country, and for others, right? For example, when we are talking about in Ethiopia's case, it's different than the ones who are studying like in developed countries, like in Western countries or not. So commonly for Ethiopia, the same thing happens for male also, but the women's gap is bigger because commonly women will not continue in academy after bachelor's or like after master's because we don't have usually support from the government or like from family. That's the common thing. So it's as a girls or women, I usually recommend them to join like different mentorship programs, like to have collaborations and not to stop like asking people for collaborations or to reach people because in our culture it's not easy like to reach out for someone to ask for internship or like for collaborations or things like that. That's the common thing, but it's really a great idea like to reach out for people like to have a collaborations also if we have like support from our government like to continue like in different programs or also like I think it will also develop when like our community and our societies like way of thinking for science is different. For this is not, I think currently it's not specific for women only, but in developing countries, it's worse than the developed ones. But I think getting a support from like different groups will like improve these things. And also like sometimes not to give up on things easily, right? It's not easy, the journey in the process.
Okay, how do you convince someone who says like hard science is not for women to pursue? Yeah.
Yeah, this usually reminds me like a quote from Hidden Figures. I don't know if you watched the Hidden Figures and there is a famous quote by Katherine Johnson that says that this is not because we wear skirts, but because we wear like glasses. So this is not about like gender. Like science is about critical thinking, right? So anyone can do it if they think critically. So they may not get opportunities or chances, but it's not like even it's not a labor work or like a difficult thing. So I think if they're good in critical thinking, anyone can do it. So it's not specific for men or women.
Yeah. Thank you so much. And finally, let's hear from you any advice you have for first for women and girls who wish to pursue fields in STEM, to study further in STEM.
Yeah.
And yeah, and also can you tell us what skills they need to work on before getting to like advanced levels?
Okay, so like as someone who passed that journey, especially as an Ethiopian woman, it's not easy to reach out people to ask questions and to continue in academia path because it may not be easy, but I really encourage them, like as I mentioned earlier, to join like different mentorship groups, collaboration groups, and also to reach out people just randomly. If we are interested on research topics, we should send them an email, like to ask them, like, can I work on internship on this topic with you? Because I have received a lot of emails from people from different countries in Nigeria, South Africa, or other countries, but it's not common for Ethiopians. So it's rejection is not a problem. So it's fine if someone says no, or they don't have like money, or they don't have time, or something like that. But it's good to ask. And I really recommend people to be critical thinkers. If anyone is good in critical thinking, they will be good in science. They shouldn't be genius or smart. So that's the main like skill needed in science. The other thing is good like to ask questions also, like different questions than the usual people ask. So it's good to ask questions and to take time to read, to discover, to explore, like things like that. So also data analysis and mathematics also will contribute, especially in astronomy, in addition to physics. So I really recommend people to develop these skills.
Okay. And what about the opportunities out there? People usually want to pursue and study astronomy or fields related to STEM, and then they don't usually get the way, or as it's not that common in our country, so they want someone to show them the way, what opportunities there are out there. If you can tell us a bit about that.
Okay, so I think the opportunities will be different, like depending on the stage of our life. For example, if we are in undergrad, it's good to look for summer schools or internship, or like people to work research also, like in Ethiopia even. There are people who works in astronomy or in other STEM fields. It's good to like look for collaborations, or to look for like internships or things like that if we are in undergrad. But if we are in masters or PhDs, there are different like funding opportunities, scholarships, like all over the world. So it's good to look for like these types of opportunities, especially for women in developing countries. I think there are also specific organizations like Organization of Women in Science in Developing Countries, OWSD or something like that. That's common. They will fund masters in like PhD also, like in developing countries. There are also like TAWAS, I think. They have also like funds for women in developing countries, even in masters in PhD. So there are different like options. So if we explore, like if we take time to explore all over the world, there are like different options of like working groups, also like fundings in fellowships all over the world, even scholarships also specific for African women, like specific for sub-Saharan African students or things like that.
Thank you, Feven. And in the chat, I think Haile Mikhail has asked if you recommend someone studying at your institute or pursuing a PhD there.
Oh, to study in my institute? Yes, I really recommend that. But like this really depends on the fund. Like it's different from universities. So the supervisor should get a grant from like European Union or from the Polish like Minister of like Education. So they should get a fund from that, and they will accept students like for different. We have like small research groups, not that much bigger, but I really recommend if you get like a good PI and a good grant.
Okay, so let us see if the audience has questions for you. For my end, I'm left with just one question, which I'm going to ask you at the end.
Okay.
So if any question from the participants. Yeah, you can ask about her research areas or any advice or any question you may have. So I don't think there are questions. So the final question will be anything you want to add, anything that's left out for your presentation in our interview. And tell us if you have a role model or someone you can tell us who inspired you to pursue this and who were the people you were looking to get here.
It took me back. So when I was in middle school, well, I think I remember when I was in grade 6, I started being interested in astronomy for the first time. So my role model at that time was like astronomer Leggesa Watro. Dr. Leggesa Watro was one of the role models, and the other one was engineer Kitao Jugo. So because I didn't know, like I didn't have a specific knowledge about space science and astronomy, but I am interested in space at all. So I wanted to work on space. So I was like, I have only like limited access to these people. So I was literally interested in space at all. So Engineer Kata Ujugu was a big inspiration for me, also like Gasawatro. But after that, I get a lot of mentors and role models in life. So there were a lot. But okay, I really recommend people not to dream small because from my experience, sometimes like our current situations or like the things which we see around doesn't make us to dream bigger because it looks like limited, but we shouldn't. So like I think someone said this, your dreams are valid wherever you came from. So it doesn't, it shouldn't be limited based on like your current situation or your current location or anything. So you should dream big and you should work hard to achieve that dream. Like dreaming is not only enough, but you should work hard also to achieve that. Also, as I mentioned earlier, don't be afraid to ask questions, to reach out people, like to ask like different opportunities. If they don't have, they will say no. Otherwise, it will be fine because you will get a chance to join two different like research groups, internships, or summer schools. Even currently, we have different opportunities because we can access anything like online, right? So it's good to reach out to people, like to look for opportunities and to reach out for people, to send an email, like short email will be easier. And so it's good to reach out to people and to look for opportunities. So don't give up, like, and don't dream small because currently you have like only limited access.
Yeah, thank you. It's a really great piece of advice for people here and for people who are going to watch your video later on YouTube. And I really want to thank you for joining us, for your time and for sharing your experience. And I wish you a great end as you're finalizing your PhD. Yeah.
Thank you for inviting me also.
Yeah, thank you so much, and thank you for joining us. Yeah. So we will wish to hear a lot from you in future programs. Yeah. It was a really great session. Thank you all.
Oh, thank you so much.